Okay, last time we started to take a look at the wave nature of light and other electromagnetic waves. What we're going to do today is to take a look at another very, very important characteristic of light, and this brings us to section 25, which is entitled The Reflection of Light Mirrors. Okay, first, let's imagine we've got some source of light. Maybe a light bulb or something like that. So here we've got our light source, and we can think of this like dropping a pebble in a body of water. It creates these waves that then propagate away from the light source. Let's imagine that we draw in kind of the peak of these waves. So as these waves propagate outward from the source, we have these circles of peaks of the wave. Let's draw those peaks in. So we have these waves that then travel outward from the source. So something like that. Rather than looking at the peaks of the waves, we can also look at the direction these waves are traveling. So rather than looking at just these peaks that are then expanding outwards, let's imagine that we actually draw in the direction these waves are traveling. So something like this. They would always be perpendicular to the lines of maximum. These lines, when we look at these are what we call the wave fronts. While these lines, we'll call these the wave or the light rays. So these are just two different ways of looking at the propagation of the waves. For us, we will be focusing on the light rays. What are the light rays doing? Basically, they will be going from the source and then in whatever direction the light is traveling. Let's imagine we now look very, very far from our source. Here we can see these are all emanating from our source here. Let's imagine we come very, very far over here. Those circles, the wave fronts, are getting bigger and bigger and bigger. The radius of those circles are getting bigger and bigger. Way over here, they will look something almost like flat planes. Imagine if we got very, very far away. These circles are so big that we can barely even see the fact that they're curving anymore. So we end up with these almost flat wave fronts. The rays also will then be basically straight lines coming from some source that's very, very far away. They will essentially look like parallel lines. So when we have a situation like this, again focusing on the rays, when we want to imagine that we have a source that's very, very far away, we'll basically imagine that we've got rays that are coming in parallel. So parallel rays basically means a source that is very, very far away. Now, I want to ask, how do we see something? When we say that we see an object, what do we really mean? Now, I don't mean physiologically what's going on in our brains for the most part, but I want to emphasize an important point. Let's imagine there's some source. Okay, here's a candle flame or something, and our source is creating these rays coming from it, and our eye is over here, so that's your eye. The rays come toward your eye and enter your eye. Now, they enter your eye at a slight angle between them, depending on how far away the source is. Your eye, or your eyes, take those rays in, and by focusing them on your retinas, your brain kind of moves those lines or traces those lines back to the point where they came from. So this is very important. Your eyes take these rays and trace them backward to figure out where the source is. Now, this might seem a little odd, but the source doesn't really have to be there. If the light entering your eye is still following those lines, your eye will still think that the light is coming from a point back here. Now that might seem a little odd. I mean, how is that possible? But let's just accept that as long as the rays entering your eye are exactly like this, your eye will think they're coming from a point back here. Okay, so we'll come back to that later on. Now, what happens when light actually strikes a mirror? What happens when light is reflected? Well, most of us have probably seen mirrors before. I have a mirror here and I have a light source. Now, to make it a little easier to see, I'm going to turn some lights off here. Which one shall I turn? Like that?
Yeah, that's it.
That's good? Okay.
Yep.
So here I have a laser that's creating a nice straight line, and I'm going to reflect it off a mirror. And here's a mirror. And what we see is that when the light hits the mirror reflects the light back. Now, one thing I want us to notice is that when the light hits the mirror perpendicularly, so when the incoming ray strikes the mirror in a perpendicular direction, that light is reflected right back on itself. However, when the light strikes the mirror at not exactly a 90-degree angle, but something a little bit less than a 90-degree angle, the ray is reflected back at another angle. And the more, or maybe I should say, the less I decrease the angle from the mirror, the more that ray is reflected back at another low angle on the other side. Okay, so can we see that? All right, there we go. Now, let's look at that a little bit quantitatively with a diagram. I'm going to draw mirrors with a surface, and then I'm going to put some hatch marks on one side. This is to indicate the backside of the mirror. While the side without the hatch marks, this is the reflective side. Now let's imagine we have a ray of light coming in, striking the mirror, and I'll indicate the incoming direction like this. That ray will reflect off the mirror, something like that. To describe how this reflects, I am going to use a perpendicular line to the mirror here. So this is a normal line. Remember, normal means perpendicular. So that line is perpendicular to the surface of the mirror. This ray will reflect according to a very, very simple law, probably one of the simplest laws there is in physics. We'll define the angle between the incident ray and the normal. We'll call that theta sub I. That's the incident ray. The angle between the reflected ray and the normal, we'll call that theta sub R. That's the angle of the reflected ray. The ray reflects according to what we call the law of reflection. And the law of reflection states that theta sub R is equal to theta sub I. The reflected ray is equal to, the angle of the reflected ray is equal to the angle of the incident ray. Okay, so what happens when we have light coming from an object? So different rays coming from an object striking a mirror. So let's put the mirror over here. So now we'll draw it vertically with that as the backside. And let's imagine that we've got our source, and I'm just going to draw an arrow as our source over here. So let me move it down a little bit. Let's look at a number of different rays coming from our source. What are these rays going to do? Well, each ray will strike the mirror and reflect according to the law of reflection. So if we have a ray coming in straight and that strikes the mirror perpendicularly, it is going to be reflected right back perpendicular. A ray that comes in at a small angle will reflect back at a small angle. A ray that comes and strikes at a, I'm going to extend my mirror here a little bit, and strikes at a larger angle will reflect back at a larger angle. A ray that comes down this side will be reflected on that side. Now the question is, what if you are over here and you're looking at the reflected rays? So you are just looking at the rays that are reflecting off of the mirror. Well, what did we say before? Your eye will take those rays and trace them back to their source. But their source, you will think, will be back here. Now, if you do this very, very carefully, it will turn out that all of these rays, okay, let's do this a little bit more carefully. There we go, something like that. All of these rays will come back to the same point back here, which turns out to be the same distance behind the mirror as this thing is in front of the mirror. When you look in the mirror, you will think that the light is coming from some place behind the mirror as opposed to in front of the mirror. This thing is what we will refer to as the object, while this is what we will refer to as the image. Now, to get an idea of this, what this really looks like, let me set up a little mirror and we'll take a look. Okay, so here I've got set up a little Batman statue here. And here is a mirror. You can see this is just an ordinary mirror. But I've actually got another Batman back here behind the mirror. So what I want to do is I want to look at the Batman in front of the mirror, and then I want to see how that Batman reflects off of this mirror. Now I'm just going to rotate this. Let's see what happens. Now, what I want you to notice is that the two Batman are the same distance in front of the mirror as behind the mirror. However, when we look at the reflection of this Batman, the reflection appears to be in the same position in space where this Batman is. So as this goes back and forth, we notice in the mirror that the reflection seems to our eye to be at the same position where this one is back here. So we'll use these two to kind of figure out what the reflection, or what we'll refer to as the image. Now, the Batman that's in the mirror, that we see in the mirror, we'll refer to as the image. So how does the image compare to the object? Well, let's notice that they're both upright. In other words, this Batman is standing up and the other Batman is standing up. They are the same distance from the mirror, one in front of the mirror, the other behind the mirror. But one thing that's very, very interesting is the object has his right arm up, while the image has his left arm up. So the reflection is what we will call left-right reversed, or we would usually call it a mirror image. But we'll call it left-right reversed. Okay, let's go back to the board. Okay, so what are the characteristics of the image? Well, first thing is it's upright. We won't say it's right side up or upside down, because what we're doing is comparing it to the object. If the object is upside down, if the image is upside down, well, then that's the correct orientation, or, well, I won't say correct, but that would say the upright. As long as it's the same as the image, we'll say that it's upright. Upright just means the same orientation as the object. The image has the same orientation as the object. The second is it's the same size. The image was the same size as the object. We'll make that a little quantitative and say that the magnification is equal to 1, plus 1. The 1 means it's the same size, plus 1 means it's upright. If we had something that was the other way around, we would say inverted. So if it's upright, it's not, inverted. It's not inverted. If the image were inverted, we would say the magnification was negative. Okay, but in this case, it's upright and same size, so the magnification is plus 1. Next, they are equidistant from the mirror. The image was the same distance behind the mirror as the object was in front of the mirror. And then finally, we said they were left-right reversed. All right, there we go. Those are the main characteristics of the image for a flat mirror. So this was all with a flat mirror that wasn't curved or anything like that. If a mirror is curved, we'll see what happens next time. Now, there are some interesting things that can happen when we have multiple mirrors. So let's imagine that we have two mirrors that are perpendicular to each other, with the reflective side on the inside of a corner. So we might think of this like the floor and a wall, or the wall and a ceiling, or something like that. Now, what would happen in this case? Well, imagine we have a source, say, over here. I'm going to extend these mirrors a little bit. Okay. Light from the source reflecting off the top mirror will create an image up here that is equidistant, well, let me do that a little bit better, that is equidistant above the mirror as the object is below the mirror. The light reflecting off of this mirror will create an image on this side of the mirror that is equidistant behind this one as this one is in front of it. But what about the rays that reflect off of this mirror that seem to come from this image that then reflect off of this mirror? Well, these rays seem to be coming from this object. It's an image for this mirror, but now it's an object for this mirror. This mirror will create an image of this object over here. So we actually get an image of an image. This is an image from this mirror of this object. This is an image of this object from this mirror. Well, this is an image that's created by a reflection off both mirrors. And if this is at a 90-degree angle, rays that reflect off this mirror and then this mirror will also seem to come from that image. So it's an image of an image. You might have seen something like this if you'd ever been in a changing room or something like that that has mirrors at an angle. It helps you kind of see behind you to see what the back of your clothes look like or something like that. We could actually imagine adding a third mirror to this where we have another one, say, perpendicular to both of these. We can imagine this might be like the inside corner of two walls and a ceiling, or two walls and a floor, where we actually have three mutually perpendicular mirrors. Well, in that case, if you can imagine the rays in 3 dimensions here, let's imagine what would happen to a ray that comes in here. It would reflect off this one, and maybe reflect off the top. The ray would actually come back exactly parallel to the ingoing ray. Especially if there was a third ray, then it doesn't matter what the incoming ray is. They would all come back out parallel to the ingoing ray. So here I have three mutually perpendicular mirrors, and this is called a retroreflector, because any ray that comes in is reflected back parallel to the incoming ray. Now I can demonstrate that a little bit. I'm going to shine this laser, and here I have a blue laser. I'm going to shine this at the retroreflector, and you'll notice that it gets reflected back to my hand, and I can rotate this retroreflector. I'm trying to keep it pointed at the same time, and you'll notice that the ray is reflected back to my hand. Can you see it there on my hand? That it doesn't matter how I turn the retroreflector, the ray is always reflected back towards my hand. This creates kind of an interesting result when you actually look at it. Now, you can see that there's a camera reflected off of the mirror. And now, if I bring this in and move it around, you'll notice that the aperture of the camera is always at the corner, no matter how I rotate the mirrors. So the aperture is always being reflected straight back, no matter how I rotate the mirrors. That aperture is always reflecting right back at you, you might say. If you were to look at this, your eye would always be right at the corner where those mirrors come together. Now, just a couple more things, some interesting results. What if we have mirrors that are actually not at 90-degree angles? So imagine we have two mirrors like this that are not at 90 degrees, and we have a source in between, something like that. Well, we get some very odd results. This mirror creates an image up here. This mirror creates an image down here. This mirror creates an image of this one down here. This mirror creates an image of this one up here. This mirror would create an image of this one over here. This mirror would create an image of this one down here. And essentially what happens is you get this collection of images going around in a circle, and if you have ever been in a situation like this, you'll see many, many images of yourself. Sometimes you're facing yourself, sometimes you're facing in another direction, and you can sometimes changing rooms have mirrors like this so that you can kind of see what you look like from different perspectives. Something else that you might have run into is what happens if you have two mirrors that are parallel to each other but with reflecting surfaces facing each other. And maybe you're standing right here. Well, you see an image of yourself over here, and then this one creates an image of you over here, and then this one creates an image of you over here, and this one creates an image of you over here, and you end up with images of images of images, and you just see this continuation of yourself or someone standing next to you just kind of going off to infinity, just over and over and over, all of these different images of images of images, etc., etc. You might have seen something like that. And all of these come back to the law of reflection. That the reflected angle, remember, as measured from the normal, is equal to the incident angle. There we go. Next time, we'll take a look at some applications of this with curved mirrors, and we will see that curved mirrors have some very, very interesting applications.